locally derived country rocks or an exotic variety. The exotic inclusions are commonly primary textured gabbroic and noritic rocks, and less commonly pyroxenitic and peridotite rocks. Sulfides occur as disseminated blebs of pyrrhotite, chalcopyrite pentlandite, or as massive sulfides with inclusions.
Offset dikes, or the quartz diorite bodies, occur as radial and concentric patterns around the Sudbury structure. In this particular area, we are looking at the Coppercliff offset dike, which runs approximately in a north-south direction, and we are standing here just about on a contact between the dike and the adjacent Creighton granite. Here we are looking at the chilled margin of one of these quartz diorite dikes, and the chilled margin itself is considerably wide. It is very fine grain. It has long needly pyroxenes, such as orthopyroxene and some clinopyroxene, and a fine grain ground mass of plagioclase, quartz, and granophyre, and some biotite, so that mineralogically the quartz diorite rock and the main mass norite are essentially similar. The main mass, or the interior of the dike, is characterized by numerous inclusions, generally of the country rock. Where the inclusions are concentrated in masses, as what we see here, there are some disseminated mineralization. The ore bodies in particular are associated with concentrations of inclusions of this character, and that the mineralization can be either disseminated in character or massive. Where the sulfides are massive, there are usually a number or a variety of inclusions present, including a variety of country rocks which are present in the environment, and also exotic inclusions. The Sudbury Igneous complex is a composite body in which a number of units are recognized. The lowermost unit is a noritic rock, and on the north range we refer to it as the felsic norite, and the stratigraphically higher unit is the quartz gabbro, which is transitional into the noritic unit, and then above that there is a thick sequence of granophyric rocks.
Within the felsic norite there is no layering, but cryptic mineralogical layering has been detected, so that there is a noticeable increase in the enrichment of iron stratigraphically higher up, with the corresponding loss in calcium and an increase in alkalis and silica. Transition from felsic norite to quartz gabbro is marked by the disappearance of orthopyroxene and the appearance of magnetite and apatite. Stratigraphically higher up, the felsic character of the quartz gabbro becomes pronounced and passes in some places almost imperceptibly into micropegmatite or the granophyric rock. The transition from the quartz gabbro or the felsic part of it to the granophyric rock is characterized by a variety of country rock inclusions. The main mass granophyre is a coarse grain rock rich in granophyre but contains minor plagioclase and up to 10% mafic minerals. The mafic minerals are highly altered to amphibole or chlorite, but locally there are relics which indicate that the original mineral was an iron-rich pyroxene. Within the granophyre, a distinctive plagioclase-rich variety has been noted, particularly at the upper half of the member, where it is in sharp contact relationships with the granophyric main mass. This plagioclase-rich variety is more calcic and mafic than the main mass granophyre, and mineralogically and texturally resembles the upper part of quartz gabbro. It is possible that it represents a detached portion of the upper quartz gabbro during emplacement of the granophyric-rich magma.
We are now going to look at the Onaping Formation.
We are now here on the contact between the micropegmatite or the granophyric rich rock on my right side and the basal breccia of the Onaping Formation on my left side.
The Onaping Formation consists of 4 members: the basal breccia, melt rocks, gray and black members. In the past, these rocks have been variably interpreted as glowing avalanche deposits, as conglomerates, as tectonic breccias, or even as chilled phases of granophyre. We would like now to present a different view in the light of some of the more recent studies on these rocks. The basal breccia is the lowermost member and has abundant evidence of shock metamorphism. These features include planar elements in quartz and feldspars, and vitrification textures after feldspars, quartz, and other minerals. The vitrification after quartz and feldspars is taken to indicate that originally these minerals were shocked to glass in a solid state or reached mescalinite stage of shock metamorphism. The gray Onaping member is a thick sheet of crudely stratified pyroclastic-looking material. It is composed of variably shocked country rocks in a variety of glasses and a fine-grained matrix of glass and mineral fragments. The glasses are flow-banded and are chemically inhomogeneous, as would be expected in a highly shocked rock that reached a melting point, but were quenched before they got a chance to become homogenized. They do not show the typical welded texture of glowing avalanche deposits, but rather show truncation of flow lines in the glass fragments, as suggesting that they were relatively solid at the time of deposition. The gray Onaping member is coarsely stratified over several hundred meters scale, but has no small scale bedding. The black Onaping member overlying it is crudely stratified in the lower half, but in the upper half there is ample evidence that it has been reworked by water. The ingredients in the black Onaping are essentially the same as in the gray Onaping, but in addition there is some carbonaceous material in the matrix. The black Onaping has a variety of structures referred to as mud balls, which are commonly developed and seem to be a characteristic feature of it. It has been suggested that they originated by flight of glass or country rock material through an incandescent cloud. The melt rocks are found as flows or intrusive bodies above the basal breccia or in the gray Onaping. They are igneous textured, commonly quenched, locally vesicular, and carry a variety of country rock inclusions. As in the other units, the country rock commonly have well-preserved shock features. The igneous matrix is interpreted as a highly shocked rock that melted and formed a fairly homogenized mass that behaved like an igneous rock. Their overall chemistry is similar to that of a mixture of gneiss, granite, and minor gabbro.
This is the Unwatton Formation, and it lies above the Onaping Formation, and the contact is gradational and conformable. The formation is about 600 meters thick, and it consists mainly of argillite and siltstone with some minor greywacke beds. Locally, there is a carbonate chert member called the Vermilion Member. The formation is characterized by abundant carbonaceous material, and there are thin pyrite layers up to about 10 centimeters thick, indicating that the formation was deposited in under pelagic conditions where bottom waters were anoxygenetic. The formation is characterized by a well-developed slaty cleavage, which you see here. The cleavage here is almost vertical. The bedding is almost horizontal, so that the bedding plane, the strike of the bedding comes across here like this. While we're looking here at rocks of the Chelmsford Formation, this formation is about 900 meters thick, but the upper portion has been removed by erosion, so we don't know the original thickness. Also, the formation was once much more extensive, presumably, than it is now. The contact with the underlying Unwatn Formation is gradational and conformable. The formation consists of mainly greywacke. Also, it has some argillite and siltstone, and it's a proximal turbidite sequence with current directions that follow the axis of the Sudbury Basin, and they travel in a southwesterly direction. The formation contains a number of structural features, including concretions, slab-like fragments, channels, current marks, ripples, convolute laminations, lode casts, flame structures, and biogenic structures. In this particular outcrop, you can see a single turbidite bed. The bottom of the bed is at the base of the hammer here, and you can see it over there. And the top of the bed, this particular bed, is here. This portion from here to here corresponds to Bauma's A interval, and this portion here would be the C and D. The individual beds are generally 1 meter in thickness, but they can be as much as 5 meters in thickness. One of the characteristic features of the Chelmsford Formation are concretions, and they consist of, they contain more iron and carbonate than the surrounding rocks, and they weather out a characteristic brown color. They come in a variety of shapes, including an elliptical shape, as you can see here. However, most of them are more or less cannonball in shape. This concretion that you see here shows that the bedding from the adjacent rocks carries on right through the concretion, showing clearly that the concretion is a replacement feature. This is an example of lode casts developed on the surface of a bed in the Chelmsford Formation. This is an example of a convolute lamination, convoluted laminations in the Chelmsford Formation. And what happened here was that the underlying layer here is also highly convoluted and deformed, and then this overlying material was deposited, and this in turn became convoluted. At this location, this bed here, where it is convoluted, is about twice as thick as over in this direction where it is not convoluted. An example of a flame structure in the Chelmsford Formation. Notice the graded bedding here. An example of a siltstone clast in the Chelmsford Formation. This is an example of fracture cleavage in the Chelmsford Formation, and it's the same structure as the slaty cleavage in the Unwatn Formation and the tectonic foliation that's developed in the South Range Onaping Formation. We're looking at the bedding plane in the Chelmsford Formation, and this rather intricate pattern that you see represents quite probably biogenic structures. They have a rather complex pattern with branching arms, and some of these arms have small knobs on the end of them, such as here, and here are some more branching arms here and here. And it's quite possible that these represent the imprints of something like seaweeds. While we're standing here on the site of the old Errington No. 1 shaft, this is one of 3 Errington shafts. Number 2 and number 3 are follow a long strike down this direction. There was also another shaft over here called the Vermilion Mine, and these were zinc, lead, copper mines, which had a checkered history. They were operating in the late 20s, early 30s, and then they reopened in the late 40s and early 50s, and had been shut down and dismantled since that time. The main ore minerals were sphalerite, galena, and chalcopyrite, and the average grade was about 4% zinc, about 1.3% lead, and about 0.94% copper. These deposits are located in a member of the Unwatn Formation, and this member, referred to as the Vermilion Member, consists of carbonate, chert, and chert breccia, and it's locally about 40 meters thick around this area, and then of course it thins to nothing at other locations. The deposits are considered to be related to sedimentary exhalative phenomena. In other words, they were deposited on the floor of a small lake or sea that occupied the site of the Sudbury Basin, and the ore minerals and the chert and carbonate and so forth were deposited locally on the floor of this lake or sea. Here we have an example of the mineralized chert breccia, and notice some of the fragments here are rather large. Deformation in the basin has developed a tectonic foliation and lineation in the rocks of the Onaping Formation in the South Range and in the East Range. Here we see fragments which have been tectonically elongated such that the long axis is more or less down the dip of the foliation. During deformation, recrystallization of the fragments has eliminated many of the features of shock metamorphism.
And now we would like to leave you with a few thoughts which we think are important in trying to understand the origin of the Sudbury structure. On both the North and South Range, the rocks in contact with the Sudbury Igneous complex have peculiar features which are not in agreement with a domal configuration as proposed by some earlier investigators. On the South Range, the strata are vertical or overturned to the south, and on the North Range, the gneissic rocks have been apparently brought up from lower levels. The fact that such gneisses occur as a relatively thin band around the Sudbury Basin in itself suggests that they are related to the Sudbury structure itself. The presence of such gneisses and the overturned strata are consistent with the proposed meteorite impact model for Sudbury structures, but in itself are not necessarily diagnostic of impact by meteorite. However, rapid excavation by meteorite impact could lead to overturned strata at the crater rim and push up or cause to rise deeply buried rocks by isostatic adjustment or even partial melting. The development of abundant and ubiquitous Sudbury breccias distributed peripherally to the Sudbury Basin leaves little doubt that the brecciation process is genetically related to the Sudbury structure. Furthermore, the presence of shock metamorphic features in the Sudbury breccia clearly points to a direct relationship to shock metamorphism and helps to explain at least some varieties of Sudbury breccia in the Sudbury area. We believe that the massive, finely pulverized, and the igneous textured varieties of Sudbury breccia could be a direct product of shock wave, and the flow-lined brecciated variety could have resulted during the isostatic adjustments after excavation of the crater. The shock metamorphic phenomena are now widely accepted even by geologists who do not believe that Sudbury structure is related to meteorite impact. I might add here that even at present, some investigators accept only the shock pressure effects in minerals and disregard the shock temperature effects. In the Sudbury structure, it is estimated that some 75,000 cubic kilometers of rocks have been affected to some degree by shock metamorphism. If shatter cones are taken as evidence of shock metamorphism, then the volume of shocked rock increases several times this figure. Of the total volume of shocked rock, more than half is represented by massive rocks and Sudbury breccias. The remaining portion is represented by the breccias within the Onaping Formation. The basal Breccia member could represent either an autochthonous or in part allochthonous breccia developed by the shock wave along the crater wall. The gray Onaping member is interpreted as variably melted, shocked, and pulverized country rock which was ejected from the crater, and eventually a small portion of it returned to the crater as a blanket of